hand over the session to Gopal Madhubushi sir for conducting the session. Over to you, sir.
Thank you very much, Dr. Joseph, for your very kind introduction to myself and to Dr. K. Balan, Professor K. Balan. You're overly generous in introducing us in the magnificent way you did. It gives me great pleasure to welcome everybody to this session. We got 3 keynote speakers, all very, very, very distinguished, and it gives me great pleasure in welcoming all of them. And I'm sure our knowledge and the boundaries of our knowledge will expand after the hearing to these 3 eminent speakers. There's a slight change in the batting order. If you're following cricket, you can see that the English team has catapulted once again to the Australian bowling. Keeping that in mind, we thought it's better to send a very strong batsman up front, which is Professor Saivanikoli. I'll introduce him first, and then we will come back to Professor Hesham Naggar and my own dear friend Krishna Reddy towards the end. It gives me great pleasure to welcome and introduce Professor Saivanikoli. We speak the same language, I believe, but I shall stick to English just for this purpose of introducing him and keeping the diaspora in mind. Dr. Saivanikoli is a professor of the Department of Civil Engineering at the University of Ottawa in Canada. He received his PhD in 1994 from Saskatchewan, I believe, specializing in unsaturated soil mechanics and its application to geotechnical engineering. Vanapalli has authored and co-authored more than 400 research papers, gave 25 keynote addresses in several national and international conferences. I myself heard him at least a few times, once in my own hometown, Kakinada, I believe, when he attended the IGC conference here. Throughout his research career, he received and has been nominated for several awards. Most notably, he won the Sturmac Award in 2010 and awarded for his outstanding services and contributions to Canadian Geotechnical Society, Georges Glinsky Award for Canada, Excellence in Research in 2015 from University of Ottawa. He is the TC6 committee member, which is on unsaturated soil mechanics, and this area is growing quite a lot in recent years, especially with the development of the unsaturated soil mechanics models, particularly in Spain. Dr. Vanapalli's research studies focus on the design and analysis of geotechnical structures such as pavements, shallow and deep foundations, slopes, soil nails, retaining walls, you name it, he has done it. Dr. Vanapalli takes pride in his teaching and serving as a mentor for many of his students who have successful careers. More than a dozen of his former PhD students and postdocs are currently are professors in universities across Canada as well as around the world. I could speak more, but I'm sure you want to hear a lot more from Professor Vanapalli than me. So I shall invite, with that introduction, which is very brief for his accomplishments, to pass the baton to Professor Vanapalli to deliver his keynote lecture. The floor is yours, sir.
Thank you very much, Dr. Gopal. Very nice and friendly introduction of myself. I really appreciate it. Let me share the screen. Are you able to see the screen?
Yes, sir. You probably want to go to, we can see, yeah, perfect.
Yeah. Okay. Well, today, the title of my presentation is Use of Artificial Intelligent Methods as a Tool in the Prediction of Soil Water Characteristic Curve. As Dr. Gopal has already said, that unsaturated soil mechanics is being implemented in engineering practice more widely. And Now I am combining my previous work on soil water characteristic curve and taking it to the next step to see how artificial intelligence models can be used. Let me first acknowledge my co-author, Mr. Yao Li, who is doing PhD under my supervision. And I appreciate the opportunity that Indian Geotechnical Society gives me, and also thanks to the opportunity that IGC 2021, which is excellently being organized by Muthukumaran and his team. Well, the presentation will go as follows. I will give an introduction. It might be a little longer, just to give the background also along with it. And then I will provide a methodology of how AI can be used. And I will provide some results and conclusions, and also very briefly discuss the ongoing work and also the future works, and show a couple of references that were used in developing this particular work. And this work is going to be, is under consideration with Indian Geotechnical Journal, and it might be published in the special volume. Well, if you see this whole map and focus on yellow and orange regions, you can clearly see that is the region where more than 60% of the world population is situated, and most of the development is actually taking place. And here you have lots of soil structures to be constructed, and the soils are typically in a state of unsaturated condition. When you say unsaturated condition, what it means is you are going to have mainly more evaporation than infiltration, and the soils are typically in a state of unsaturated conditions, and the negative pore water pressures prevail. But in humid and temperate regions, the well-established saturated soil mechanics are used. I always try to show this slide, especially when I do a presentation in India, to talk about the Panchabhuta. The soil behavior is significantly influenced by energy, water, air, and space, and all these things would have an influence on the properties of the soil. So indirectly, Panchabhuta gives a much more rational explanation of the behavior of the soil. So the soil, in other words, soil atmospheric interactions can be explained using unsaturated soil mechanics, because the main parameter that actually changes is the soil suction, and the soil suction can be used as stress state variables. In other words, all the 5 elements that I have discussed can be used here. So in this picture, in the world of soil mechanics, what you see here is most of the structures are actually placed in unsaturated soils. However, we use the well-established soil mechanics, which considers mainly saturated conditions. A framework for the interpretation of unsaturated soil has been provided in terms of 2 stress state variables by Professor Fredlund and Morgenstern, which gives you a much more reliable explanation. So here I'm showing you a shear strength envelope, which clearly shows that the shear strength is influenced by both the net normal stress as well as the metric suction. So the frontal plane here is the saturated plane, but when you have suction, there would be a different characteristic behavior. The shear strength would be having another parameter called phi, and that has to be taken into consideration. But if you want to interpret, for example, shear strength, you have to do extensive testing. And if you see these pictures, it clearly shows this testing is not easy, it is expensive, it is time consuming, and you have to train the people to get reliable results from it. So in the last 20 years, soil water characteristic curve is being as a tool. It is the relationship between the degree of saturation and soil suction. And as the soil suction is increased, for example, if the drying is taking place, what happens is there will be various phases that would be developed. And due to this, the there will be a non-linear behavior of the shear strength of unsaturated soils. I'm focusing only on shear strength just to explain, but the quotient of permeability also can be related to the continuity and the tortuosity in the liquid phase in the unsaturated soils. And for example, the shear strength and volume change behavior would be related to the interface contact area controlling the stress transfer. If you try to see here in the saturated soil, the path is the least, but however, when you're coming to unsaturated soils, the length increases, and by the time we're in the residual zone, what happens is water cannot actually escape. The only way it can escape is through the vapor phase. So soil water characteristic is linking this to the actual properties of unsaturated soils. Many models have been developed for predicting the shear strength, or there are also similar approaches for permeability, etc. But even this soil water characteristic curve is not that easy, and you have to use equipment which takes a lot of time, sometimes days and sometimes weeks. So therefore, soil water characteristic curve is also not that easy, and it requires expertise, and many parameters actually influence the behavior of soil water characteristic curve. Therefore, simple techniques have also been developed for predicting the soil water characteristic curve. There are 4 different methods, and the physico-empirical methods are some of the important ones because they actually help in trying to understand how the pore spaces, which are related to how the water flows, and also this pore space interface, how it influences, as I have shown you in the other figure and explained the permeability behavior, would actually influence. So that you can introduce the scaling factors and also introduce or use some of the soil properties, and then have these physical empirical models to actually predict the soil water characteristic curves. There are also statistical estimations and artificial intelligence models. This is recently getting a little bit more attention because all the data that can be generated can be used, and we can be able to predict. So there are simple methods that have been developed, but here we are proposing mainly how the entire soil water characteristic curve can actually be predicted. Others have provided only comparisons between the values of estimated volumetric water content and and the measured volumetric water content. So the last approach is the correlation that, that can be developed using the fitting parameters of the soil water characteristic curve. There are many other methods in the literature too. And in many scenarios, what we do is we fit the soil water characteristic curve, and I'm highlighting 2 equations, Van Ganisten's equation and Fredland and Sink equation, which are well established in the literature and very widely used. In this study, we have used the UNSATA database, which has been published by Nemes and Hess Research Group. This is available for everyone. All the properties are there. The soil water characteristic typically, as I said, can be plotted as degree of saturation versus suction, or even volumetric water content versus suctions. And you can see here there are 3 important phases: boundary effect zone, transition zone, and residual zone. There is a method that can be actually used to predict what is the air entry value and residual suction. I'm not going into the details. Vanapalli et al. 1998 provides a simple technique similar to Casagrande's method for getting these values, but the computational techniques have been developed for that. There is also relationship between the grain size analysis and the soil water characteristic. If you try to see here the shape, there is a strong relationship between the soil water characteristic as well as the grain size analysis. So the flow takes place through the pores of the voids that you have in the soil, and that information can be gathered from the grain size analysis, and that is what we do in the soil water characteristic curve. So therefore, there is a strong relationship, and that can be used even in artificial intelligence techniques. And if you try to see here, I have highlighted some of the points in the soil water characteristic curves. in the grain size analysis that can be used. If some data is missing, you can use an interpolation technique, and that can be used. So the data of, there is data of sand as well as clay. So we use MATLAB. My student has developed a very comprehensive program that can be actually used. Here, I'm highlighting the data. We have used Unsaturated database, and also for some verifications, we have actually collected some information from the literatures for the verification purposes. If you try to see here, various soils information is given that is mainly used from the database to form the training set and the testing set. So here I have I have gathered some information from a source with different artificial intelligence models. So here, as we all know, it mimics the human behavior in some way, and then try to use some interpretation using the machine language. And there can be various types of, there are various types of machine languages or some machine learning tools that are available. And along with the data, we can have a little deep learning circuit that you can be used, and later on using the data mining and combined with the computer science, we can predict whatever we want. There is a black box in it. We will be discussing in a little while. Basic framework actually consists of data preparation and pre-processing. So we have used Unsaturated, which is the data processing. There are various AI models. We have used only two, excuse me, ANN and Mars. I will go through them. So here, I'm not going to any all the details. In the slide, you can have the information. So artificial neural networks is vaguely inspired by the biological networks that constitute animal brains. And you can see from this picture that once you have the input and we use ANN mathematical tools, you can get the output using the input information. That means the input information is the key here. And what happens is once the input is provided, using whatever model that you use, ANN or Mars, there are hidden layers. And in that, the machine language develops the interrelationship. So there is like this hidden layers is like a black box. We don't know what really happens, but it understands the interrelationships and it provides the output of whatever we want using the input information. So the input information that we give should be related to what we want. So here in the hidden layers, you can see here using the information of the input layer, you can have 10 input layers or 20, whatever we wish. So here you can give the weightage, and the weightage can also be gathered by the program that you develop, and the activation function, which is the black box, but it develops the relationship. You can also understand, give a bias, trying to give which would be the preferred one, and we get the output, whatever we need. So giving a brief idea of ANN structures, I can use linear or sigmoidal. We use sigmoidal because in unsaturated soils, you have nonlinear variation. I'm not going to go into all the details because I have a lot more information to actually cover. So the Mars equation actually compiles all the data, and then he gives a mathematical equation like it. Mars would be using the spline function, which would be having various knots. It's something like a tree. At the knots, you have the hinge, and the hinge, you can provide more information. It's like branches, and that type of technique has been developed by Friedman, and that has been used. So one thing, one of the limitations of the Mars is it gives a mathematical equation, but the interrelationship of the properties is not really understood. So I have already said that there is a hinge function which works as a knot, and you can have various groups. You can have you can have two or more hinge functions such that you can take more information and then develop a relationship with what we want. So complex relationships can be analyzed. For example, unsaturated soils, which has nonlinear variations. And using this background, if you try to see for the sands, we used ANN model, artificial neural networks. You can see that there is a good comparison between the predicted and the measured water contents, the volumetric water contents. So here in the Mars model too, we had a reasonably good comparison. Some data is falling outside, but still it is a reasonably good comparison. In all the cases, it is more than 0.8. So now in the Mars, we will be generating an equation. And here, depending upon how accurate you want, you can add more information or less information as input parameters. And here you can see 3 input parameters are used and the mathematical equations have been developed. And for sandy type of soils, you can see here the prediction between the measured and the soil water characteristics of measured and predicted values are actually shown here. So you can see some of them are good, some of them are not good. It doesn't understand anything. It just gives a relationship. So therefore, it is not, it is okay, but there are some limitations. We also used outside the database, and you can see that Galaj, Utimura's data and Shai et al.'s data is used. Some of them are good, some of them are not good. We have used for a clay sand. In this case, you can see R square is 0.3. That is not good because whenever you are having clay, you can see the clay behavior would be influenced by fabric, and therefore the R square achieved was not right. So therefore, the model that has been developed here is not taking the influence of clay, and only predominantly the training data is of sands. And from sensitivity analysis, 2 types of sensitivity analysis have been done to evaluate. In the first group of sensitivity analysis, if you try to see here that if we have taken away one of these parameters from the grain size analysis, but if you are taking away the information of soil suction, then what would happen is R square value would come down, both in Mars model as well as ANN, but you can see that R square value would be very high when soil suction information is used. So in the second group, we used only 2 input variables because the soil suction here, we realized is the most important parameter. To understand the next important parameter, we used only 2 parameters and then have seen that there are some information from the grain size analysis that is more important. So what we had to do is, well, it is okay, it is reasonable, but still, what is there a way to improve? So we can use advanced algorithms, but also if you are giving the model a little bit meaning using physico-empirical model, we have used ARIA and Paris models. It introduces the scaling factor and explains the pore structure of the soils in a reasonable way. And we combine both these approaches to develop what is called artificial intelligence aid design method, and using the established concepts of soil mechanics. So in simple terms, the proposed artificial intelligence aid design methods combines the AI models, and we have used Mars because it gives a mathematical equation in which you can add all the information from the grain size analysis, and then we combine with the traditional soil water characteristic models fitting the soil water characteristic here. We also have a scaling factor to adjust the soil water characteristic curve using the Mars model. And this is achieved through ARIA and Paris model. Later on, we actually use the same data for fixing using a mathematical function proposed by Ferdinand and Sching in 1994. This gives you a smooth curve. To try to see when you're combining all these things, you have a much better comparisons. And here only the information of grain size analysis is actually used. It is rapid once we develop a program, and it is reliable, it is inexpensive. Only we need the grain size analysis information. The summary is we propose Mars model, and for scaling factors, we have used ARIA and Paris, and then smoothen the curve using Fredlin. Advantage is only simple information of grain size analysis, but disadvantage is it depends upon the model, artificial intelligence model, and it is like a hidden box. Well, the technique is simple and rapid, and we have showed for the coarse grained soils. Now I'm going to the fine grained soil. The approach is exactly the same, but the data that would be used for Trey type of soils, 70% of the data is used for training, and testing has been corrected using the remainder 30%. And you can see here the R-square values are 0.8. And again, similar to what we have discussed, we had in the Mars model, we have developed this equation. So using the data, you have a very comprehensive equation, but that can be used for any type of data of the for the fine grained soils. And here the BF actually refers to the basic function. And here we have used a few parameters from the grain size analysis along with the soil suction. And if you are comparing these things, the R-square values are varying from 0.88 to 0.97. And now we did some sensitivity analysis similar to what we have done for the coarse grained soils too. So I'm not going to go into greater details. Again, suction is an important parameter. For the fine grained soils, we have seen other two parameters. So this, we can, if you wish, we can use only these parameters, and then instead of having a much bigger complex equation, you can still achieve reasonably good comparisons. And you can see here, if you are removing the information of suction, what would happen is R-square values comes down. Suction is a very important information. And here we have seen that P50 information, when you add, it provides a much better correlationship. Again, the approach for the fine grained soils is the same. From the data set from the grain size analysis, you can choose what are the important parameters. We have used only 3, but we also tried other ones. There was not that much of difference. We used the spline function, and to give a physical meaning, we have used ARIA and Paris model, and then we have fit it with the Fredlin-Zink equation, which gives you a smooth curve. So ARIA and Paris model, as I said, it is a scaling factor, alpha AP, ARIA and Paris model. The physics behind this equation and the mathematical relationship is given here that has been used. But when you're using fine grained soils, we have to predict the soil water characteristic curve such that you have all the 3 zones, the boundary effect zone, the transition zone, and the residual zone. So you have to know what is the end suction range. And for that, we have used the data from Shin et al. And we developed a simple mathematical relationship. And there is an upper bound value and the lower bound value, but we have used the average value, which is equal to 0.6. So this would mean that once you know the suction range, you can predict the soil water characteristic curve from 0 value of soil suction to this value, which is the residual suction value, such that you have the information of all 3 important zones, because the soil behavior, unsaturated soil behavior, is different in boundary effect zone, transition zone, as well as the residual zone. So this is what we have done. And if you try to see here in the AI design method, which actually means we use either ANN or Mars, and then we use a physico-empirical model like ARIA and Paris, and later on we can combine with Fredlin and zinc equation. So there are 3 steps. First, if you try to see here, we use Mars, and the experimental data points are orange, and the green is the one that we actually get from the Mars model. And that constitutes the first step. In the second step, to provide some physical meaning, we use the ANP model. We can calibrate the alpha AP from ARIA and Paris paper information. And based on this, afterwards, what you can do is, if you can actually combine the data, what you can see here is that there is a reasonably good comparison. We have used a very limited data. We have used only from UNSODA. That's not much data, but we also have checked other data too. There's a reasonably good comparison. The worst one that we have seen is 0.73, but many of the things are 0.86 or higher. Sorry, in the range of 0.85, in and around 0.85. So to conclude, this, as the data is, more and more data is available, we have an opportunity to compile all this information, and we can group them and then try to ask the computer to predict your soil water characteristic curve for the coarse grained soil or fine grained soils. We have separated right now using limited data, and we were able to reasonably predict the soil water characteristic curve, both for coarse grained soils and fine grained soils. But many parameters actually influence the soil structure, loading, and other parameters. We did not get into all those details, but we have a preliminary package that we have actually developed. So for fine grained soils, we need the information of residual suction, and we have developed a simple tool to predict the residual suction, and you can use that suction range to actually get the soil water characteristic information. For coarse grained soils, the upper limit suction value is used as 100 kPa, but typically in sandy type of soils, by the time you have a suction of 100 kPa, you will be seeing that all the soil water would be completely removed for the most part. We're also working to predict the entire suction range from 0 suction to completely dry condition, which is 1 million kPa, and also take into account of the various factors, how the soil structure and fabric influences, how the loading influences, how the chemical parameters influence, such that we have a reliable soil water characteristic prediction. So these are the references that have been used. I have completed my presentation a little earlier because I was fearing that I need 45 minutes, but interestingly, I have finished 1.5 minutes. So if you have any questions, I would be glad. So there is more time for Gopal to ask questions, and I will try my best to bat as per his expectations, and hopefully, if not century, I would be able to get a good score, which would be more respectable. Because he called me a fine batsman.
I'm sure you did a fantastic job in presenting such complex material very clearly for us. Thank you so much. And also thank you for keeping to time. As you said, you still have a minute to speak if you wanted, but I appreciate you keeping to time and giving more opportunity for questions.
I'll take some more time because I have the time. I acknowledge all the work is actually done by the students. This would not be complete unless I thank my mentor, Professor Fredlin, and many of my students who have worked, and they have moved to various professions right now. And these are some of my recent students. Okay, thank you.
Thank you, Sai. I'm kind of hoping that some questions will appear on the chat box. I hope that's the system they got. But while I'm waiting for that, I wanted to ask you just one quick question, I think. Admin stepped in. Hello?
Are you able to hear me, Gopal?
Yeah, I can hear you. You're
Okay.
able to hear me as well, right?
Yeah.
Okay, let me ask you my question. One thing I was always interested in with unsaturated soil mechanics is the soil behavior. Normally, we come from this Camp-Clay model and the critical state soil mechanics. Now, that's complicated enough when we have fully saturated clays or sands to deal with. In your mind, how does the stress-strain relationships change? Stiffness is one thing. You talked about the changes in stiffness, but how about the stress-strain behavior? Would you get, with the increase in strength and stiffness, do you get smaller strains when you have partially saturated conditions? And a subsidiary of that question is, say you designed a structure based on the current partial saturatedness or unsaturatedness of the soil, and then because of the, say, climate changes and other global warming and the rest of it, you get more rainfall or more heavy rainfall. Would the behavior change significantly?
Of course, definitely it changes. So therefore, when we are developing models right now, taking into account of the climate change, we just cannot really depend on one parameter. In my belief, I think we have to actually have a unified model. The unified model which takes into account of freeze-thaw conditions as well as wet-dry conditions. So we have to have a constitutive model which would be able to capture this. So right now, we were very focused in trying to really explain the behavior with some experimental results which satisfies one criteria. But we are in this particular time, because of the climate change, you have to take into account, and we have to develop, for example, the relationship between the soil water characteristic curve for the drying and wetting and freezing and thawing. And in all these things, energy is the key parameter, and the energy has a strong relation with suction. So we have to develop it. We don't have a unified model. Such a unified model with having a link with a constitutive relationship without introducing any parameters like fitting parameters, such a thing. This is a dream, but sometimes we have to dream. Star Wars, okay? Even the movie was a dream, but it has some things where we have seen things have actually happened along those lines. So if we, because we have very powerful computers and we have very smart students, and we have definitely much better tools than what we have even 5 years ago. I think it is possible. The future is great. And I think we can do it. So we have DEM methods. We are considering into account of, you yourself are an expert in finite element techniques. We have to have this type of constitutive models, but in the constitutive models, we cannot have too many parameters. If we are understanding the mother nature, I am pretty sure that we can nail down and identify some key parameters and get the general behavior of the soils, irrespective of freeze-thaw, wet-dry conditions. I believe it.
Very good answer. Thank you for clarifying that for us. Are there any other questions? I'm not able to see on my screen if there are any other questions for Dr. Vanapalli. Professor Madhav, do you have a question? I'm sure I'm doing this right.
I hope that Only you and I are not talking. I hope
that's fine by me. I got an opportunity to talk to you. That's great. Anil?
Fine, sir. Fine. It was an excellent presentation.
Are you able to see any questions for?
No questions in the chat box, sir.
Okay. Very good. In that case, Dr. Vanapalli, thank you so much once again on behalf of the IGC conference and personally from me. Thank you so much for keeping to time and addressing such a complex topic in a very succinct manner so that everybody can understand. And I'm particularly impressed with the way you handle the artificial intelligence as a black box, the AND models and so on. And it's very, very important to have some physical sense when you're employing such methods. And I'm a great believer in that. Thank you so much for that. Our next speaker should be Hesham. Have we got him?
Yeah, he's there, sir. Sir has joined in.
Hello.
Hello. There you are. Hello.
Good morning.
Good to see you.
Good to see you, Gopal. Long time no see.
Yes. I'll try and be professional, and because we are being recorded and whatnot, I'll try and be as professional as I can, and we can have a chat maybe afterwards, sure. You and I. Let me do the introduction first. So our next speaker is very distinguished and a good friend of mine, Dr. Hesham Naggar. He is a distinguished university professor of Western University, Canada. He is the editor-in-chief of Soil Dynamics and Earthquake Engineering, one of my favorite journals, and he was the past associate editor of Canadian Geotechnical Journal as well. He's published very widely, over 450 technical papers, book chapters on foundations, soil structure interaction, and geotechnical earthquake engineering, and consulted on major projects worldwide. He's the main developer of software Diana 6 used worldwide for design of foundations for dynamic loads. He received numerous awards, including Geosynthetics, Sturmac, Meyerhoff, Canadian Geotechnical Colloquium Speaker, Western University Distinguished Professor, Faculty Scholar Award, Outstanding Teaching and Research Excellence Awards, as well as in 2015, Ontario Professional Engineers Medal for Engineering Research and Development. He's an elected fellow of the Canadian Academy of Engineers, Engineering Institute of Canada, and the American Society of Civil Engineers. I know this is a very small introduction to such a great professor and good friend, but with that small introduction to introduce you to our listeners, Hesham, the floor is yours, and you have 30 minutes to deliver your keynote lecture for us today on helical piles, I believe.
Thank you so much, Gopal. I really appreciate your kind words. I will start sharing my presentation right now. Where is it? That's weird. Where is this? Oh, maybe.
Yeah.
Yeah, can you see it now?
Yeah, we can see it now. If you can put it into presentation mode, then we can see the full screen. Yeah. That one, yeah.
Okay, very good. So,
Hesham, just hang on a second. If you, I think it's going to, we are seeing the speaker's view so that we can speak we'll see the next slide as well. So if you go to the display settings, I believe, and just say,
yeah, I know. Why is this so?
I see you have 79 slides, but you have only 30 minutes.
Don't worry about that. How is that now? How is that now?
No, it's still the same. Oh, yeah, it's better. Thank you.
Okay. Thanks.
Yeah,
So,
it's okay.
good evening, everyone. It's early morning for me here, so please bear with me. Today's presentation is about the dynamic and seismic response of helical piles. Helical piles is a foundation system that is very old, but has started a new life recently, has been widely used in many applications, and certainly in North America, we started to use it in applications that involve dynamic loading, seismic loading, and I see in Europe also they introduced it to support of large wind turbines, and I actually have seen some work considering it for offshore wind turbines where you support very large lateral and bending moments as well as the axial loads. So it's become a very important foundation system, and the reason for that, it's very easy installation compared to pipe driving and even drilling. Doesn't produce any vibrations or any associated noise. And as I said, it can be installed very quickly in industrial installations. So in many of these applications, you will see significant dynamic loads. You will see seismic loads if it's installed in seismic regions. So we started to focus on the response of helical piles under dynamic and seismic loading. And today I will show you some of the most recent results we had. But if you want a fuller description of the work we have done on this, I can share that with you through emails afterwards. So today I'm going to talk about some of the shake table tests that we've done on helical piles and the results we obtained from that. So we started by doing some shake table testing, large scale shake table testing on reinforced concrete piles in liquefiable and non-liquefiable soils. And there you see the setting here, a pile group of 4 piles supporting a model superstructure and was subjected to large shaking as well as small shaking to establish the dynamic characteristics of the system, and large shaking to observe the behavior of the pile group between liquefiable and non-liquefiable soil in a comparative study. So there was the first time that someone looks at the behavior of the same system under conditions of liquefiable soil and non-liquefiable soil, so you can identify the effects of liquefaction on the pile group. The shake table model was heavily instrumented with pivotal pressure transducers, with accelerometer shape readers, strain gauges on the piles, accelerometers to measure the acceleration of the ground and the structures. So it was really heavily instrumented, as you see here, which allowed us to observe the different phenomena that happened during the shaking. The applied seismic loads, or the ground motions, I should say, we have some white noise, as I said, to establish the dynamic characteristics. We also used a sine beat wave as shown here, and then we applied the wind-shown Wollong earthquake that represents strong ground motion to allow liquefaction to happen and observe the behavior of the foundation system during liquefaction. As I said, we instrumented the model heavily, and here are some measurements of the pivotal pressure taken at different times under the effect of different earthquake signals. So for the small shaking, you see here some generation of the pivotal pressure, but the maximum pivotal pressure ratio is less than 0.2, so definitely there is nowhere to approach liquefaction. However, under the strong earthquake shaking, let's say the readings at the water pressure transducer number 4, it approached 1 here, and same here at the pressure transducer number 7. So it approached liquefaction. So we see the evidence that the soil reached liquefaction, then we can actually look at the behavior of the pile foundation accordingly. Now, as I said, we have a comparative study. So we have the case of dry soil, non-liquefiable soil, and we have the case of saturated soil where liquefaction occurred. And we see here water spouts and sand ejection due to the liquefaction, while here when the ground is dry, liquefaction didn't happen, but you can see ground fissures due to the excessive accelerations that occurred and amplified through the ground. We evaluated the acceleration amplification from the bottom of the shake table to the top of the soil box. And as you see here, we've seen for the case of dry soil, amplifications as high as 7 times the input motion here. For the weak motion and for the strong motion, the amplification reached almost 4 times. Interestingly enough, that we found for the case of strong ground motion in liquefiable soil, we actually had the amplification. So you see for the case of site 1, which is the liquefiable soil, you see de-amplification has happened, while for the case of weak ground motion, we have seen some amplification about 30%. So that is very interesting. That was the first observation we made in comparison between the 2 sets. It's exactly the same soil bed. The only difference between the 2, that in one case you have liquefaction and the other case you don't. And we see in the case when we don't have liquefaction, we have de-amplification of the acceleration. For the case we have no liquefaction, we have seen some amplification, actually significant amplification. We also looked at the soil lateral displacement in both cases for the weak ground motion. So here in the weak ground motion, the soil displacement, we are talking about the range 6 to 7 millimeter. When we have liquefaction, we have a strong shaking, both liquefiable and non-liquefiable soil, the displacement of the soil increased as we expect and reached as high as 18 millimeter for the case of non-liquefiable soil. For the case of liquefiable soil, we've seen actually it's interesting that the ground movement was a little bit less than the case of non-liquefiable soil. In terms of the dynamic response of the piles, again, for the weak ground motion, you see the pile in the liquefiable soil has seen larger displacement, larger acceleration compared to the pile in the non-liquefiable soil throughout the profile, so over the length of the pile. And for the case of strong ground motion, you see the difference is larger now because the soil liquefied and the shaft lost most of its lateral resistance. So you see significant increase in the acceleration here compared to the case of the non-liquefiable soil. We also instrumented the piles to measure the strain and use the strain to determine the bending moment in the piles. And as you see here, based on the strain gauges readings, we see a maximum bending moment happening at levels M5 and M7. So that's M7 and M5 here. And here, M7 is close to the interface between the liquefiable loose soil, loose sand, and the dense sand that did not liquefy through this process. So the bending moment was actually concentrated near the interface between the 2 layers. We also have seen a large increase in the bending moment at the interface between the clay crust and the loose sand layer. We also observed the behavior mood or the deformed shape of the pile structure system. And as you can see here, for the case of the pile in liquefiable soil, we've seen the entire system is rocking. So because most of the soil here lost its strength, then the pile groups start to rock as a whole. For the case of non-liquefiable soil, where the dense sand contained the ends of the piles, you start to see significant deformation, and you see shifting of the structure almost laterally, and the piles experience significant bending moment as opposed to the case when the soil liquefied. We also compared the seismic response between the case of rigid ground, or the fixed base case that we always consider in an analysis of structures, and the behavior of the structure when it is situated in soil. So this superstructure model is exactly the same as this one, but is connected directly to the base of the shake table. So it's not in the soil. It represents the case of fixed base. And we have the same structure here supported in the soil, and we compared the response between the two. We see here the structure is made of two concentrated masses connected with flexible beams. And then during the shaking, we monitored the acceleration of the different masses using these accelerometers. And we see here the structural response component now. So for this case, we'll see here the dynamic displacement, and we decomposed the components of the dynamic displacement to a cyclic component and monotonic component. So as you see here, the monotonic component increased with time. So in essence, the superstructure continuously increases in tilting, while the cyclic component, you see oscillation about the mean part. And that demonstrated the level of displacement that could occur through the seismic shaking for the structure. And as you see, the structure have seen significant displacement here, about 37 millimeter. That is the monotonic part, the part that accumulates, as opposed to the shaking part, the cyclic part that was experienced by the structures. For the case of the structure on fixed ground, as you see, the response is totally cyclic, meaning the structure will vibrate about a mean position, but will not experience permanent displacement as we expect, because the ground will come to a final position as the starting position. So we see the difference between the liquefiable soil will lead to significant displacement. For the structure in non-liquefiable soil, we'll see some permanent displacement at the end, but most of the response is oscillative in nature. And then for the structure on fixed ground, we'll see only cyclic behavior and no permanent displacement. And here also we see the cyclic and monotonic displacement components for the time histories, as you see how it varied with time. Now this shows more the tilt at the end of the earthquake shaking. This is the structure on the table itself, and as you see, there is no tilt. And then this is the structure in the ground, and you see how it tilted relative to its original position. So it shows here the significant rocking behavior that happens for the structure in liquefiable soil, which could actually lead to the failure of the structure, even though the piles themselves did not fail, because in most of the studies that we've seen for structure supported on pile and shake table test, the focus is always on the failure mechanism for the pile as a pile, but we see here that the piles did not see bending stresses that can lead to failure. However, the structure itself started to tilt, and if we take the proportions of the tilting that happened to this structure, a prototype structure will actually collapse due to this level of tilting. So that shows the seismic instability of the pile support structure due to liquefaction. As I said, the structure tilts and eventually can collapse because of the significant tilting that happens. Here we also look at the lateral soil displacement. So this is some sort of lateral spreading, and this is interesting because the layers were all horizontal. The surface of the soil was horizontal. The interface between the different soil layers was horizontal, but yet we observed some level of lateral soil displacement. So this is a phenomenon of lateral spreading. And we always observe in the literature the ground is horizontal, and if the interfaces between the different soil layers, especially the liquefiable soil layer and the stable soil layer, is horizontal, you don't anticipate lateral spreading, but still we observed here some level of lateral spreading. It's not very significant, but you can see here some level of lateral spreading, one millimeter here. But given the scale of the experiment, that represents some significant lateral spreading that was observed in this case. The other thing, we looked at the distribution of the soil resistance on the pile, because the next part of that we will establish, if we want to call it PY curves, to represent the liquefiable soil resistance during the earthquake shaking. So we established the subgrade reaction and lateral soil force acting on the piles, and you see here that distribution of the soil resistance for the non-liquefiable soil, you see high soil resistance. And for the liquefiable soil layer, you see the soil resistance is much smaller, but it's not zero. And that is the interesting part, that in many of the studies and in practice, even when the soil liquefies, many engineers I see in practice tend to say the liquefiable soil offers no resistance whatsoever. But our observation here that the liquefiable soil resistance, as you see here, is actually not zero. So we have some resistance that can be counted on. And if you remember, I showed you the pool water pressure reached the excess pool water pressure ratio reached 1. That means the soil has actually liquefied, or for most of the profile, but we still see significant soil resistance. We also looked at the seismic behavior of the pile, and we decomposed the response of the pile into a component related to the ground motion, so the horizontal displacement of the ground, a component related to the deflection of the pile, and a component related to the rocking of the pile group foundation. So for the structure that sits on the table directly, you see the only ground motion component plus the flexural component of the response of the system. But for the case of the pile foundation in liquefiable soil, we've seen translation and rotation. So the rocking component actually contributed significantly to the response, as we see here. And we determined the displacement for different grounds for fixed case. So here for the case in saturated site, very large displacement, as I mentioned before, 37 millimeter. And that was primarily due to the rocking contribution of the behavior. And here's the dry site. The displacement increased up to almost 25 millimeter, but it is mostly oscillatory in nature, and some smaller permanent displacement for the structure sitting on the base of the table. So this represents the fixed base case. As you see here, the oscillation about the initial position of the structure. We also looked at the behavior, and we developed some model for the structure. So we established the mode shapes of the structure. So the first mode shape is a cantilever deflection, and then the second one is the deflected shape, as we see here. And we looked at the response between the different cases. And we see here the increase in the shear force relative to the rigid base case, and you see a significant increase in the shear force and the maximum bending moment. Also a very significant difference in the response with the rigid base case. For the case of site 2, where we are in dry sand, you see the base shear for the structure is almost 3 times higher than the case of the base shear for the liquefiable site. And that is a very interesting observation. As I said, oftentimes if we look at the seismic forces and structure, and that what really matters to us, then for the liquefiable soil, we see here the base shear is only 30% of the base shear for the structure on non-liquefiable soil, but still the performance of the structure in the liquefiable soil was much worse. We also have seen significant increase in the bending moment in the non-liquefiable soil compared to the liquefiable soil. But again, as I said, the behavior was much less because of the rocking vibration mode structure. So these are the observations from the test. We used that to validate numerical models, and then we used the numerical models to observe behavior under different cases, because the shake table testing was limited in the parameters that could vary. So what we did, we developed the finite animal models. We used the geotechnical parameters interpreted from the shake table test. We calibrated the numerical models, and then we used different levels of ground motions to observe what happens if we have stronger ground motion, what happens if, let's say, in the axial resistance of the piles, what happens if it liquefies or it doesn't liquefy. And we also looked at helical piles behavior in this case. We satisfied all the boundary conditions. We used the same loading as the shake table testing. And as you see here, a comparison between the numerical model in the non-liquefiable soil and the numerical model in the liquefiable soil. So there are a good match between the two sets, which give us confidence in the ability of our numerical models to predict the behavior. And we also compared the prediction of the water pressure throughout the soil model, and it showed good comparison. We also compared the acceleration of the soil. We compared the lateral displacement of the soils and the piles. So all over the numerical models were able to reproduce the observed behavior during the shake table test. And then we started to look at the different components of the behavior of the piles. So we looked at the kinematic interaction effect versus the inertial interaction effect. So we look at the component of the, if we see here for the strong motion, when you have different levels of peak ground acceleration, 0.3, 0.4, 0.6, and we see the increase in the bending moment. So this is the normalized bending moment as a ratio of the bending moment capacity. And we see, due to the kinematic interaction effect, you can have very significant bending moment through the pile profile for the pile in the dry ground and much less value. So here are the values compared. As the level of shaking increases, you see a significant increase in the bending moment. When we increased the pile diameter, is this the case here? So this is the pile diameter of 0.3 meter. We see a significant increase in the bending moment because now the pile is more rigid, and when it is rigid, it can actually support the soil more, and that leads to a significant increase in the bending moment. So we found that increasing the pile to deal with the shaking actually leads to a significant increase in the bending moment, and has to be designed accordingly due to that kinematic interaction that we may not actually consider. Here, we are considering, again, the kinematic interaction without the superstructure. This is for, again, a pile diameter of 0.3 meter. That's 3 times larger the pile diameter in the experimental sets. And again, we see here as the peak ground acceleration increases, the response increases as we expect, but same as what we've seen for the smaller diameter pile. So increasing the pile diameter didn't really help in this case because the pile moved with the soil. Now this is the saturated site. You see a very different behavior when for the saturated site. Interestingly enough, you see the level of normalized bending moment here reach the capacity of the pipe. So the pipe could actually fail due to the kinematic interaction in this case. I know I'm approaching the end of my time. So we found that pipe bending moments.
Still have 5 minutes.
Oh, okay.
You're good.
Okay. So the pipe bending moments increased with higher PPA, and the increase in saturated site is significant relative to the dry site due to the loss of lateral support of liquefiable soil. The maximum bending moment occurs at the interface of the loose and dense sand, and we've seen that many of the reconnaissance of piles that failed during earthquakes. The failure happened at the interface between the liquefiable and non-liquefiable soils. The inertial interaction due to the superstructure mass contributes the most to the bending moment at the pile top, and the interface of the top clay and loose sand in this case, so the stable soil and the liquefiable soil. Piles with larger diameters experience a significant increase in bending moment, and that was kind of a very interesting observation to make. Due to the kinematic interaction, we've seen that bending moment increased almost 3 times due to the increase in the pile diameter. And the bending moment distribution corresponds to the case of rigid pipe behavior, because now the pile diameter is larger, so the pile starts to kind of rotate more than flex due to the low slenderness ratio. The pile lateral displacement increased with higher PGA. However, the piles are displaced laterally as a rigid body in the saturated sand. And again, this represented rocking behavior, which led to very strong displacement of the supported. Now we look at the interesting part for the axial behavior of the piles that we never looked at, and here we make reference to the good work of our dear colleague here, and we observed this factor of safety relationship that published by Professor Madabushi. And we actually assessed the variation of the factor of safety liquefaction as the soil liquefies along the pile shaft. So we look at the axial forces during the shaking along the pile. So we see here the static resistance. This is the static shaft resistance along the pile here. And then during the shaking at different times here, you see the reduction in the axial resistance along the shaft, but it's not going zero. So that's interesting. So it decreased, but it didn't go to zero. So that actually supports the this factor of safety for liquefiable soil as proposed by Professor Madabushi. And also, I don't think I will be able to get to the contribution of the tip resistance of helical bias, but we see here is the axial force again at different times, and we see how the axial resistance it changes. When the axial resistance decreases, we see the end-bearing resistance. I'm having difficulty with this one. So here is the end-bearing resistance increases. So as the shaft resistance decreases, the bearing resistance increases, which compensates for the loss of the shaft resistance. So as long as we make sure that the pile tip is in a stable soil that will not liquefy, we can actually find that the axial capacity is not the problem. It is going to be the settlement that is going to be the problem, or the tilting of the structure that is going to perhaps jeopardize the integrity of the support structure and for the pile foundation. We looked at the effect of changing the pile diameter and its axial response. And this is the soil resistance, the excess pore water pressure for a 0.1 meter diameter pile. And this is 0.3 meter diameter pile. And you see that the pore water pressure in all cases reached a very high level, 1.2, greater than 1. That means that actually the pore water pressure caused liquefaction. But what we found as the pile diameter increased, when the shaking happens, it creates a gap between the pile and soil, and that allows the path for the water to flow in that region and cause even more liquefaction. So you see here, in all cases, the soil approached liquefaction for the larger diameter pile because of the gap generated between the pile and soil, which will allow the water to flow near the pile shaft, and that's where the pressure transducers were placed and it monitored higher liquefaction. So that was very interesting to see that larger diameter piles may not actually lead to better performance because of this case, because it will concentrate the liquefaction around the pile, then the pile loses resistance and then starts to rotate in rigid body movement. I don't know. It's not. Oh, here it is.
It's nearly your time is nearly.
And then I'm the end of my time, and I accept that. Sorry about this. That's not collaborating. But anyways, I'm open to questions, and as I said, I can share more of the information with the audience afterwards. So I'm available for questions.
Thank you so much, Dr. Naggar, for that excellent presentation. It's a topic, as you know, I'm very, very interested in, and I'm sure a lot of Indian colleagues are also very interested in. In fact, I wanted to ask you a few questions myself, but there is one from the audience. Professor Bhubinathan has a question, and it came on the chat, and it says,
yeah, so I see here about the design of piles in liquefiable soil, and I see you actually responded to that correctly. Yes, you can design piles in liquefiable soil as long as you have some competent soil underneath the liquefiable soil. Yes.
Yeah, I thought while you're talking, I can share my views, but I'm sure people want to know your views. If you want to elaborate on that, you can.
So yes, as I showed here in the observations, while the shaft resistance decreases significantly due to liquefaction, two observations we make. The first one, it doesn't really go to zero. So there is still remaining some shaft resistance, even when the soil reached full liquefaction over the entire shaft length. The second observation that we found that the end-bearing resistance increases as the shaft resistance increases. The reason for the increase in the end-bearing resistance, that when the shaft resistance decreases due to liquefaction, the pile settlement increases, and as the pile settlement increases, mobilizes more of the end-bearing resistance. And that increase in the end-bearing resistance compensates for the reduction in the shaft resistance, and we end up with the seismic factor of safety, if we want to call it this way, of the pile is still greater than 1 and the pile doesn't fail. But the observation we'll see is increased settlement. This increased settlement was necessary to mobilize more end-bearing resistance, which compensated for the shaft resistance. But as I said, the issue here becomes is to observe the level of settlement that could happen during the earthquake and the effect of that settlement on the supported structure. The second observation, we want to make sure that we extend the pile into the stable soil at the bottom sufficiently to prevent or reduce this rigid rocking vibration mode, because as I said, for a tall structure, if it rocks too much, then that will jeopardize the integrity of the structure. So in essence, to design pile foundation in liquefiable soil, we want to make sure that the level of settlement post liquefaction is satisfactory, and also we want to make sure that we extend the piles into the stable soil sufficiently to ensure that we minimize this rocking behavior.
Okay, thank you so much for clarifying that and adding to my little comment as well out there. I can't see any other questions. There was one about the axial strain. How do you work out the axial strain in a triaxial test? But I think it's probably, we won't have time to get to that. I had a quick reply.
Just one thing I wanted to mention about this axial behavior. I didn't come to the part where we compared the response of the helical piles and the reinforced concrete piles, and we actually have seen significant improvement in the response of the helical piles, much less settlement, much higher end-bearing resistance, and the factor of safety was much higher for the helical pile because we placed the helices in the dense sand layer. So in the dense sand layer that did not liquefy, it maintained its end-bearing resistance, and hence the response was much better for the helical pile foundation compared to the straight shaft pile foundations.
Thank you so much, Hesham, from me, also from all the colleagues, and we are very grateful from the Indian Geotechnical Society that you took the time early in the morning and made this presentation for us. Thank you so much.
Thank you.
So if you stop sharing your screen, I can move on to my next keynote speaker.
Okay.
Next keynote speaker is Professor Krishna Reddy, another good friend of ours. And hi, Krishna.
Hi, Gopal. How are you?
We're running slightly short on time, so I will do a quick introduction. And
Sure.
I'm sure people want to listen to your excellent work in geoenvironmental engineering as always, more than me twittering about you. Let me do a quick introduction, and then I'll pass on the baton to you. So, I can talk about you for a long time, but let me do a quick introduction. Krishna Reddy is a university scholar, distinguished researcher and professor of civil engineering, civil and environmental engineering, director of sustainable engineering research lab, and director of the geotechnical and geoenvironmental engineering laboratory at the University of Illinois, Chicago. Dr. Reddy received PhD in civil engineering at Illinois Institute of Technology, Chicago. He received gold medal for his BE from Osmania University, Hyderabad, ME civil engineering from IIT Roorkee. Prior to joining the University of Illinois, Dr. Reddy worked as a civil engineer and project manager for over 3 years in the industry. Dr. Reddy is a registered professional civil engineer and an Envision sustainability professional. Reddy's teaching and research and consulting experience includes many different areas: geotechnical investigation and infrastructure, environmental pollution control and remediation technologies, waste management and beneficial reuse, sustainable resilient engineering. I think everybody would agree with me that Dr. Reddy is extremely well known for his geoenvironmental engineering work. He's published over 259 journal papers, more than 200 conference papers, 22 book chapters, and has over 14,000 citations. He received many awards, including the ACA Wesley Honor Award, ASTM Hogan-Tugler Award, UIC Distinguished Research Award from University of Illinois, Scholar Award, and University of Illinois Award for Excellence in Teaching. He's a fellow of American Society of Civil Engineers, diplomat of geotechnical engineering, and board certified environmental engineer. As I said, I can go on for a long time. I'll stop there and give the floor to you, Krishna. Please.
Okay, thanks a lot, Gopal, for that nice introduction, and nice to see you online. I also miss seeing all our friends. IGC has always been my meeting place to see everyone. Anyway, it's virtually is better than nothing, but hopefully we'll get back to normal in the near future. So, Gopal, can you see my presentation?
You're good, Krishna. We can see you.
Okay. So, as Dr. Madhabushi mentioned, I work in geoenvironmental engineering area. So I chose a topic I don't know, many people may not be familiar with. So there are a lot of challenges in geoenvironmental engineering. So I'm going to talk about this Electro Bioremediation. This is a technology to remediate contaminated sites, soils, and groundwater. So before I get into my presentation, I want to mention what kind of research that I do, because you've probably seen my name in a lot of different places. So a lot of my research is on environmental remediation of soils, sediments, groundwater, and stormwater. And I also work on waste management and landfill engineering. And for the last 7-8 years, I've been working on life cycle assessment and sustainable and resilient engineering. And of course, many of you know that my master's and PhD are on geotechnical engineering. So I am familiar with all the topics in geotechnical engineering. I also worked as a geotechnical engineer, a civil engineer for 3 years before joining the university. Of course, my background is civil engineering. So the first two that you see, they are geoenvironmental engineering, and the third one you see is a sustainable engineering. So my focus has been on geoenvironmental engineering and sustainable engineering. There are a lot of challenges in geoenvironmental engineering and sustainable engineering field. So anything that you do in these fields have really a huge immediate impact on practice. So that is very much satisfying to me working in this field. So before I get started, I want to also thank Professor K. Muthukumaran and also the conference organizing committee for this invitation. And I also want to thank my co-author and collaborator, Professor Claudio Camiseye from University of Vigo, Spain. We actually wrote a paper together that's going to be published in Indian Geotechnical Journal. So if you are looking for more details, many details will be in the paper that is upcoming. I want to thank my graduate students and, of course, the funding from U.S. National Science Foundation. So I know, many of you are not familiar with the geoenvironmental engineering, so I will give you a brief introduction to, problem of contaminated sites, risk-based site remediation. That's what we do now, and what are the different remediation technologies that we have. And I'm going to focus on this bioremediation because this is, very simple and sustainable technology. I will mention briefly what it is, but it has some limitations. So how do we overcome those limitations? So that's where this Electro Bioremediation comes in. I'm going to explain that one, very briefly. And this is kind of, still a lot of research is going on this topic. So I will give you the state of the situation on this technology, and then at the end, closing remark. So the problem of contaminated sites, is there everywhere in the world. In some places, you know exactly how many sites are there. Some places they didn't even start, investigating this issue. So, but it is a worldwide problem regarding these contaminated soils and groundwater. And what are the sources of soil and groundwater contamination? There could be many sources. I mean, even if you think about air pollution, right? From air pollution, you're going to have particulate matter, and that particulate matter is going to come on the, fall on the ground, and it mixes up with the soil, and soil gets contaminated with infiltration of precipitation. You can get groundwater contaminated. There are a lot of other sources of contamination. But if you ask me, one major source, that would be the land disposal of solid and liquid waste. And of course, in the US, we have waste containment systems, but in many countries, you don't have those. You have dump sites. So a lot of things will leach into the soil and groundwater and pose problems. Why do we need to worry about this soil and groundwater contamination? That's going to basically cause a lot of health issues in humans. All the diseases that you see, some of them are not explained by doctors. A lot of them are attributed to the environmental factors. And also, you are going to damage the ecology, the plants, birds, all those, surrounding environment is going to be damaged. So this is definitely not acceptable. So, we need to prevent soil and groundwater pollution, but if there is some pollution, we need to clean up the pollution. What do you mean by pollution? Pollution is basically these toxic chemicals that you are dealing with. There could be many different types, inorganic chemicals, organic chemicals, and all of them are causing adverse effects on humans and in the environment. So in the US, we have strict rules. We have to clean up a contaminated site, if it is found. First thing what you do is the site characterization. This is where you can employ all the geotechnical investigation tools, but additional tools to characterize the chemical concentrations. Then you have to do the risk assessment, health risk assessment. This is not familiar to geotechnical engineers, but this is an essential step. That you need to learn, if you want to work in this field. And then if the risk is more than acceptable, then you need to define the remedial goals and then look at, what kind of technologies are out there to use to reduce the risk. And the site contamination could vary from site to site. You may have, for example, a dump site where, you need to put a containment systems. And you may have soil contamination in the wetter zone that needs different types of technologies. For groundwater, in the source zone, that needs different technologies. And if you have a dilute plume, then that needs different technologies. That's why we have developed a lot of different types of technologies, containment technologies and treatment technologies. I teach a graduate level course on these different technologies. If you want to treat the soils in situ, there are in situ soil remediation technologies. If you want to excavate and treat it, you have the ex situ remediation technologies. And then you have a groundwater remediation technologies that you have to use based on the site conditions, based on the contamination conditions. So there is no one single technology that can solve all the problems. You have to choose the technology based on the site conditions. So if you are interested in learning more basics about remediation technologies, I suggest you to look at this book. Now let's talk about this bioremediation. The bioremediation is a kind of a nature-based solution because in soils and groundwater you have a lot of microbes already existing. So we are trying to use them for remediation. And if you have the right microbes, they can actually use the organic contaminants as a food, and then convert into basically safe end products. That's what I'm showing by schematically here. If you have a contamination such as soils and other things, and the microorganisms mediate to convert them into environmentally friendly byproducts at the end. So if in terms of the chemistry and biology, basically this process is called the oxidation reduction reaction. And in these kind of reactions, one chemical loses an electron and other gains the electron. So a lot of times organic compounds are losing electrons. So therefore you need to have an electron acceptor to take that electron. So electron acceptor is a essential thing. So if you have oxygen present, then oxygen can serve as electron acceptor. So then that whole process is called aerobic biodegradation. If you don't have oxygen, let's say if you go in deep into the ground, you don't have oxygen. In that case, you need to have a different electron acceptor. So there are different organic chemicals, inorganic anions that can serve as alternate electron acceptors. So you need to have electron acceptor for biodegradation of the contamination to occur. And this technology is nice because you can degrade all kinds of organic compounds. It could be petroleum hydrocarbons or more complex organic compounds. You can also apply to treat the metals, but you cannot really destroy or disappear metals. You can only convert mobile metals into immobile metals. So that's kind of bioimmobilization, they call it, if you are applying to metals. But organics, you are basically degrading them to into safe byproducts. Also, it sounds simple, but there are a lot of things have to be right in order for this degradation to occur. So first of all, you need to have right microbes, and then the contaminants should be available for the microbes. For example, they want to use it. So contamination, if it is not available, then they cannot use it. And you need to think about what is the contaminant structure and what is the toxicity of the contaminant to the microbes. And as I mentioned, we need to have electron acceptors, and these microbes need nutrients to survive. And also these microbes are very picky. They need to have right moisture content, right temperature, right pH, right salinity, and they don't want to have any other type of highly toxic materials, including the heavy metals around them. And so you need to have a right conditions for the microbes to degrade these organic contamination. So if you don't have the right situation, that's where the engineered bioremediation comes in. So if you don't have nutrients or electron acceptors, you provide those things through engineered systems. So that's called biostimulation. And sometimes you don't have right microbes at the site, then you can supply the microbe. That's called bioaugmentation. So you can actually implement this one in the field very effectively. You have a soil that is contaminated, microbes are already there. Maybe you just need to provide some oxygen or some nutrients, and this remediation will occur easily. So it's very simple. If you have a groundwater, again, you will have microorganisms, but you may not have right environmental conditions, maybe nutrients. So you just use wells to introduce these nutrients and disperse them through the contaminated media. So you are making those available to the microbes, and the remediation will occur. And as I mentioned, there are many advantages with bioremediation because organic contaminants are completely converted into non-toxic byproducts, so you don't have any issue going into the future. Minimum mechanical equipment is needed, and it can be done in situ as well as ex situ. It's the low-cost technology. And if you analyze in more detail, this is the green, sustainable, and resilient technologies. So low energy, low emissions, less waste, conserve natural resources, and so forth. However, there are some disadvantages. One thing is, depending upon the conditions, it may take longer time to degrade. The other thing is, some compounds, they don't convert directly into non-toxic products. So it has to go into certain sequence. And if you have a partial degradation, and at the end of the partial degradation, if you have some byproducts, those byproducts could be more toxic than the contaminants that you started with. So you need to be careful, make sure that you don't have a partial degradation of contaminants. You have a complete degradation of the contaminants. So that's one of the challenges. And you don't want to have very high concentrations because these microbes don't like that high concentrations. And I mentioned that limited bioavailability, because contamination has to be in soluble form or easily dissolvable form. That's one requirement. And you need to have nutrients and right environmental conditions, and you need to have right microbes. And also, one of the challenges with these technologies, if you have a sandy type soils, it's easy to hydraulically, introduce these things. But if you have, clay type soils or heterogeneous soils, then hydraulic methods don't work. So that's the biggest concern in terms of the field applications when you have, low permeable soils. So in these situations, bioremediation has, challenges. So it won't work the way you want it. So in order to address these limitations, we can combine the bioremediation with electrokinetics. And what is, then this technology is known as Electro Bioremediation. I worked on, a lot of research projects dealing with electrokinetics, using it as an individual technology to remediate soils and groundwater, but I'm not talking about that one. There are some issues with that technologies, but here I'm talking about using the electrokinetics to address the limitations of bioremediation. So what are we doing? Basically, you have the wells already and you are trying to introduce the nutrients, but in combining electrokinetics, basically you are putting the electrodes into these wells and applying a small electric potential. And that's all, that's the additional thing that you are doing it. And when you do that one, bioremediation is going to occur more efficiently. That's good. And electrokinetics can also offer other benefits, make the contamination bioavailable, make the bacteria mobile a little bit, in the soil so that contamination remediation can occur throughout the medium. And you can have electron acceptors and nutrients migrated, you can put it into the electrode wells under electric potential, they can be transported into the contamination media. And also, electrochemically, you can produce these electron donors, hydrogen and oxygen also in case if you need them. And then if you have metals, in addition to organics, that is the case at many sites, this can be also, remove those contaminants. So, basically when you put an electrode and apply electric potential, you're inducing these different electrokinetic transport processes. So there's electromigration, basically the ions moving, to the opposite electrodes. And then there's the bulk movement of water, due to this electric double layer effect. It's called electroosmosis. And the electrophoresis, the charged colloids, micelles and bacterial cells, they can also move. So basically you are getting the advantage of these processes when you introduce the electrodes and apply very small amount of electric potential. And in addition to those transport processes, you're going to see these electrolysis reactions happening at the electrodes. At the anode, you're going to generate the oxygen, and at the cathode, you're going to generate hydrogen. But you also generate this H+ and OH- ions, and they go to electromigrate into the soil. That's going to change the pH of the soil. So you need to make sure that the pH of the soil is changed in a favorable manner rather than in adverse manner. So that's one thing you need to keep an eye on it. And as I mentioned, this hydrogen and oxygen can be used as electron acceptors. So electrobioremediation basically is the combination of the bioremediation and electrokinetics. Can overcome, all the major limitations of bioremediation. It can degrade the organics. It can be applied to any soils. Now, low permeable soils is not an issue because you can generate the electroosmosis through those soils. So, which otherwise would not have been possible by hydraulic methods, which is good. And then, if you have heavy metals or mixed contaminants, those can be addressed. And we are not talking about making the bioremediation more complicated. Just a very simple additional equipment that you need. So overall, it's going to be cost effective. Overall, it's going to be green, sustainable, and resilient. So a lot of investigations have taken place to look at, what processes work under this electrobioremediation and what are the system variables that we need to control. So I'm showing you, different types of laboratory electrokinetic, electrobioremediation, reactors that have been used by different researchers here. One of the first questions comes when you talk about electrobioremediation is when you apply electric potential, when you apply electricity, will the microbes die, right? So will they get shocking effect? Some studies that have been done shows here, if you have 100 milliamps or 300 milliamps, you can see that this is the count, microbial count after treatment, compared to the before treatment. So if you have 100 milliamps of current, there is no issue. So when you apply electric potential for 2 hours, you have a 97. So there's a 3% reduction. And 4 hours, there is a 10% reduction. So that's taken. And 300 milliamps also, there is not much change. But if you have more, in this case, it's found to be 350 milliamps is the threshold. And you can see that, microbes die as a result of this electric shock. So you really need to think about, what is the range for applying this electricity. You don't want to apply too much to kill the microbes. That's one thing that you need to keep in mind. So you work within that, electricity range that is not harmful to the microbes. And then, so when you apply electric potential, you're going to see, these contaminations getting degraded. So for example, in this one, this is just in the water. You can put a, contaminated solution in the water and apply electric potential. So you see, there is a reduction of this PCEs contamination that you can see without electrolysis, without, electric potential. You can see that's not going to happen. And also, the biodegradation, if you can see, if you have a microbes and apply electric potential, there is going to be a substantial reduction in the concentration versus, if you sterilize, basically kill all the microbes and apply electric potential, you're not going to see that effect. So the point is, microbes are doing better under applied electric potential. And applied electric potential can facilitate transport of nutrients that are needed for microbes. So this study shows that sulfates, nitrates, ammonium can be easily transported under electric potential. But when it comes to the soil, again, there are some experiments that are done that show that, lactate is one of the electron donors that that can be transported into the soil. They did these experiments with the clay and sand. Even with clay, you can see that lactate could be transported into the soil quite well. And then the oxygen that is generated at the electrode, that can be also transported under electric potential. That's a positive news about it. Again, lactate getting transported into the soil, that will basically, enhances the biodegradation in the soil. So as you see, the lactate goes inside, and then you have a microbes, and then this PCE is one of the toxic contaminant that is found at a lot of contaminated sites, and that eventually gets disappeared. And here is the study again, another study that looked at lactate transport into the soil by electric potential that could be achieved. And as a result of that, you can see the microbial population has increased. So after 47 days of electric potential application is this much, and then the second bar that you see is after 56 days. So it's increased. Even after shutting down electric potential, then you can see that, still that biological activity keeps on happening. And as a result of that, you can see, the contaminant concentrations and the degradation pathways. Basically, you start off with the PCE, and it gets degraded into these different compounds. At the end, you end up with the methane, which is non-toxic. There are a lot of studies that look at this electro bioremediation. This is another contaminant, basically total petroleum hydrocarbon. So here, if you don't have any treatment, contaminant concentration is not going anywhere, just the bioremediation, and then you can see EK and bio, that's electro bioremediation, can really, give very positive. You need to look at how microbial microbes are changing. That can be done these days very easily with microbial analysis, and you can get these results. And again, just showing you there is an overwhelming amount of data that shows that electro bioremediation can work for different types of contaminants. And just looking into more fundamentals, you can also look at there is a shift in types of microbes that will survive under enrich under electric potential compared to other ones. So again, the other thing that I found very interesting in one of the studies is, do you have to apply electric potential continuously? So what happens if I go with bio and apply electric potential only for some time and then stop it and let my bioremediation take place, and then just a sequential bioremediation and electrokinetics. That is also found to be very, very effective. So instead of applying current continuously, you can apply for a certain amount of time and then take off for just the bioremediation to occur. And not only like a small scale lab testing, some researchers have also done it at a pilot scale, in the field, but in a small scale. And this is one study that looked at this electrobioremediation of PAHs in the field. Again, the results really overwhelmingly show that combining electrokinetics and bioremediation can really, make the process effective and also efficient. And again, the microbial, population is going to increase under this, electric stimulation. So there are very limited studies in terms of the full-scale actual applications. So there's one that is done in the U.S. So this is a site, Air Force site in Florida, U.S. And here there was a contamination. There was a spill that happened, and the topsoils are all sandy type soils. And basically, this contamination is PCE. This denser than water. Density is denser than water, so it basically sinks in. It sunk through the sandy soils, and then it entered into the clay, and it got stuck in the clay. And this is becoming a continuous source of contamination to underlying groundwater. So how do you clean up this? Of course, this is the clay, so you cannot use any wells and then use hydraulic methods to clean up. So this electro bioremediation method, is investigated at this site. So they used, several wells as, put the electrodes and some other wells to supply the nutrients. And they were able to supply, the needed nutrients or electron donors very efficiently. They even, tried to, apply some microbes also. So they were able to find good results based on this large-scale field experiments. So this is, if you look at this sketch, this monitoring well 9 is very outside, upgradient. All the treatment is happening in this box here. So if you look at the results of that upgradient, where it's beyond the treatment zone, you have this contamination, PCE present, nothing is happening there. But if you look at the monitoring well within the treatment area, you can see this PCE is the major contaminant that is there, and that is degraded into these byproducts. At the end, you want to get everything into ethane. So again, that shows that if there's an effective treatment that's happening, and that is not at one location; it's also true at other location. Also, there's a microbial characterization is also shown here. And that also shows that this works really, really well. And even the soil sampling is done, and that also shows that concentrations, PCE concentrations decrease and get into non-toxic products or butter products. Again, there's a microbial characterization is done, and you can understand a lot about what is happening to the microbes. Which microbes are doing the job. So you don't have to rely just on the contaminant concentrations, but you can look at this microbial characterization and find out which microbes are doing the job, which microbes are being enriched under electric potential. So overall, this field project is shown to be very successful. So just to conclude, the takeaway points from this presentation is, the bioremediation and electrokinetic remediation can be used individually, but combining them can be very, effective and cheaper and sustainable and resilient. And this can be applied to any contaminated soil conditions, any contaminated conditions. So this is kind of a very versatile. And the system is very flexible. It's not like a one black box that you have to use, anywhere you want it, but you can tailor it. And the equipment that you need is not special. And however, we need to have a more detailed performance monitoring stuff to look at it. If you want to know more details about this electrochemical remediation technologies, I recommend you to look at this book that we wrote, and for other remediation projects, you can look at these other books. I know I have taken out a little more time, so I may not have enough time for answering all the questions. So feel free to contact me through email, and I'll be more than happy to answer any questions that you have. Thank you very much for your patience and listening to me. Thanks.
Thank you, Krishna, for an excellent presentation. I just realized it must be really early for you. Thanks for waking up early in the morning and doing a fantastic lecture for us. I'm sure there will be a lot of questions. We don't have much time. Just going, we need to go to the valedictory function just after this. You're the last speaker of this conference. You certainly picked